Welcome to Sleepy Stories, where calm and curiosity share the same quiet space. Here, we explore the universe in a way that helps the mind unwind and the body rest. If sleep doesn't come right away, that's perfectly fine. You can simply listen, breathe a little slower, and let the steady rhythm of understanding carry you. And if these nights of gentle discovery bring you peace, consider tapping like or subscribe. It helps us continue creating calm journeys through the cosmos. Tonight, we follow light itself, the traveler that connects stars to eyes, matter to meaning. Light is not a single thing, but an ongoing process, a movement of energy that began long before there were planets or people to see it. Every beam that touches your world began somewhere unimaginable, in the deep interior of a star. Inside those blazing spheres, temperatures climb to tens of millions of degrees. At such extremes, hydrogen atoms move so fast that their protons collide and fuse, forming helium and releasing energy. That release is light in its first form, high-energy photons, packets so small yet so powerful that each carries a trace of the sun's creation. But newborn photons cannot simply fly outward. The star's interior is dense, a hot, charged plasma where electrons and ions block every direct path. A photon travels a mere fraction of a millimeter before colliding with another particle, scattering in a random direction. In this way, light spends millennia, sometimes millions of years, making its slow migration toward the surface. The journey that seems instant across space begins in near-endless delay. When at last a photon escapes the outer layers, it bursts into the openness of space. There is no longer matter to confine it, no resistance to slow its flight. Here, the vacuum reveals one of the universe's most reliable constants, the speed of light, about 300,000 kilometers each second. Every second, that distance is crossed effortlessly. Every heartbeat, light circles Earth more than 7 times. This speed is woven into the structure of time itself. Nothing outruns it, and everything we see depends upon it. In empty space, light travels in straight lines, yet the universe is never entirely empty. Gas, dust, and magnetic fields bend, scatter, or dim its passage. When a photon passes close to a massive object, the fabric of space-time curves, and so does its path, a phenomenon called gravitational lensing. Through that bending, astronomers glimpse galaxies otherwise hidden, their light stretched and magnified by gravity's quiet geometry. Even the tiniest deflection becomes a message, revealing where matter gathers in the dark. Though we often think of light as simple illumination, it carries within it the full language of physics. Each photon has a wavelength, a color, and an energy proportional to its frequency. From violet to red, from gamma rays to radio waves, all are expressions of the same electromagnetic spectrum. The visible range, the narrow band that human eyes can detect, is merely a sliver of that grand continuum. Our senses catch only a hint of the cosmos's radiance, yet that hint is enough to fill skies and memories. As light streams outward from its parent star, it spreads evenly in every direction. Each wavefront grows larger, weaker, more diluted, yet still constant in speed. A single beam crossing interstellar space may travel for millions of years before meeting an obstacle. Distances become timescales. To look outward is to look backward. When we gaze at the nearest star beyond the sun, we see it as it was years ago. When we view a distant galaxy, we see light that left when Earth was still molten. Every photon arriving here carries the imprint of an earlier universe, turning the night sky into a record of what once was. The physics of this motion is both elegant and absolute. Maxwell's equations describe light as self-propagating electric and magnetic fields, waves that sustain one another even in the vacuum. No medium is required. Space itself becomes the conductor. This is why light defines the very idea of causality. It sets the pace at which information can move, linking energy, time, and distance into one inseparable framework. And yet, within all this precision, there remains quiet beauty. Light is the reason the universe is visible at all, the messenger through which matter announces its presence. It sculpts every color, defines every horizon, and marks the passing of every day. When you watch the first sunlight reach your window, you are witnessing the end of a journey that began in a stellar furnace long before human life existed. The warmth you feel is energy released by fusion, filtered through space, refracted by air, and finally absorbed by your skin. Proof that you are connected to the stars not only in substance but in experience. As we move deeper into this voyage, we will trace light's long path, through nebulae and galaxies, through Earth's air and water, into the intricate optics of the eye, and finally into the mind that perceives it. Each step reveals how the universe converts raw energy into awareness. The tone will remain steady, the pace unhurried, the science precise yet gentle. Let the rhythm of these truths ease the day's noise. If rest comes as you listen, it will arrive like light itself, quietly, continuously, without effort. Deep within a star, light is born into imprisonment. A photon that has just emerged from fusion cannot surge freely outward. It is surrounded by an ocean of charged particles so dense that it collides again and again, each impact scattering it in a new direction. What seems like a brilliant blaze from afar is, in truth, a slow internal storm of radiation, pressure, and motion. Physicists describe this region as radiative diffusion. A photon's path is not a straight line but a random walk. It might travel only a millimeter before striking an electron, lose a fraction of its energy, and set off again. After countless collisions, it drifts outward by mere centimeters in thousands of years. The density of stellar plasma ensures that light crawls outward with inconceivable patience, a reminder that what we call sunlight is ancient before it even leaves its star. This gradual migration is crucial for stability. If photons could escape instantly, a star would release its energy too fast and collapse under its own gravity. Instead, radiation pressure balances inward compression. The steady glow we see from Earth is the visible expression of equilibrium between gravity pulling in and light pushing out. A single photon's delay becomes the reason a star can shine for billions of years. Within this vast crucible, energy constantly changes form. Gamma rays born from nuclear fusion degrade into X-rays, then into visible and infrared photons as they lose energy through scattering. Each collision lengthens wavelength, transforming destructive radiation into the gentle light that can later support life. The process is both violent and delicate, an atomic struggle that produces calm luminosity on the outside. Scientists estimate that it can take anywhere from 10,000 to 1,000,000 years for a photon to travel from a star's core to its surface. The numbers themselves are uncertain because the journey is statistical, not linear. Each scattering event is random, yet the collective effect is predictable. Outward diffusion, like heat seeping through thick insulation. The comparison helps us imagine the unimaginable, energy so persistent that even endless detours cannot stop its escape. As the photon nears the photosphere, the material around it thins, collisions become rarer, and light begins to move more directly. Temperatures drop from millions to just a few thousand degrees, changing the character of the radiation once again. By the time it reaches the surface, the photon's energy matches the visible spectrum, the familiar yellows and whites of a star's radiance. From that boundary, light finally breaks free, racing into the vacuum at full speed. This slow escape is one of the universe's quiet masterpieces of balance. It demonstrates that stability in nature often comes not from stillness but from regulated motion, forces in opposition finding rhythm. The star endures because its internal chaos resolves into outward harmony. In the same way, balance in our own systems, from the heart's beat to the breath's flow, arises from constant yet controlled energy. As the last layers of plasma thin, light becomes visible to distant worlds, beginning its voyage across interstellar space. Each photon that reaches us today has spent nearly its entire existence hidden in that interior maze. The sunlight falling through your window this morning was once trapped inside the sun's heart before humans existed to receive it. Its long escape is the reason you can see, feel warmth, and mark the passing of a day. At last, the photon nears freedom. After a journey that lasted hundreds of thousands of years through a dense interior, the outer layers of the star begin to thin. The pressure and opacity that once trapped light give way to a region where atoms can exist without being instantly stripped of their electrons. This boundary, known as the photosphere, is the visible surface of a star, not a solid shell, but a layer where light can finally escape into open space. Here, energy transforms into what we call radiation. The photons that emerge carry information about temperature, chemical composition, and motion. Their spectrum, the spread of colors and wavelengths, tells us everything we can know about the star without ever touching it. A hotter star emits more blue light, a cooler one more red. The balance of these wavelengths forms a signature, as distinct as a fingerprint. Astronomers read those patterns the way geologists read layers of rock, deciphering histories written in color. In the photosphere, light behaves according to the rules of blackbody radiation. Every object with temperature emits electromagnetic waves, and the hotter it is, the shorter and more energetic those waves become. The sun's surface, around 6,000 degrees, produces a nearly perfect white blend of all visible wavelengths. Yet when that light passes through Earth's atmosphere, shorter wavelengths scatter more easily, giving our sky its characteristic blue and our sunsets their red. Even before it leaves the star, the physics that shapes our sky is already present. The escaping photons do not move in isolation. Streams of convection rise from below, hot gases climbing upward, cooling, and sinking again in giant cellular patterns. The sun's surface boils in slow motion, each granule a column of gas several hundred kilometers wide. These motions create subtle flickers, the shimmer of sunlight that dances across water or glows unevenly through clouds. Behind every sparkle is a dynamic surface, alive with plasma and motion. Beyond the photosphere lies the chromosphere and corona, outer atmospheric layers where temperature strangely increases again. Here, magnetic fields dominate, twisting and looping into arcs that can burst in solar flares or coronal mass ejections. Photons streaming through these regions may be scattered or absorbed, adding complexity to the light that finally reaches the void. Every fluctuation in the sun's magnetism, every flare or spot, leaves a trace in the radiation that spills outward across space. When photons break free at last, they do so in every direction. They stream outward as a continuous sphere of energy, spreading wider and thinner as they go. Some will strike the surfaces of nearby planets within minutes. Others will travel for eons before touching dust or gas in distant systems. Most will journey into deep interstellar darkness, perhaps never meeting matter again. Yet even those unseen photons contribute to the galaxy's faint, collective glow. The transition from confinement to freedom is more than a physical change. It represents a threshold in the universe's behavior. Within the star, light is bound to matter, constantly absorbed and re-emitted. Beyond it, light becomes information, a message that can cross emptiness unaltered. Every observation we make of the cosmos depends on this release. When you look up at the night sky, what you see is not matter itself but radiation, energy that escaped countless furnaces long ago. In the calm of open space, the photon finally becomes what it was destined to be, a traveler. No longer blocked, it races outward at the fastest speed nature allows, carrying with it the history of its origin. Its color, energy, and direction preserve a record of the processes that shaped it. From this point on, light becomes the universe's archive, preserving in motion the story of everything it touches. Once free from their star, photons reveal their true nature, entities that defy ordinary categories. They are not particles in the classical sense, nor continuous waves like ripples on water. They are both, depending on how we observe them. This dual character, known as wave-particle duality, forms the foundation of modern physics and the key to understanding light's behavior across the universe. In one moment, light behaves as a stream of discrete quanta, each carrying a fixed amount of energy proportional to its frequency. This relationship was defined by Max Planck and expressed by the simple equation E equals hNIu, where h is Planck's constant and NIu the frequency of the wave. Higher frequency means more energy. Gamma rays strike with fierce intensity, while long radio waves carry energy so faint they can pass unnoticed through the atmosphere. Each photon is a messenger of energy, perfectly consistent and universally obedient to this rule. In another moment, light reveals its wave-like nature. It interferes with itself, creating patterns of brightness and darkness when two beams overlap. Thomas Young's double-slit experiment, conducted more than 2 centuries ago, first showed this delicate structure, proof that light moves as oscillating electric and magnetic fields, synchronized and self-sustaining. In the emptiness of space, these fields dance together, each generating the other, allowing light to travel indefinitely without a medium. This duality can feel contradictory, yet it is a kind of harmony. The particle nature allows light to deliver energy in precise amounts, while the wave nature lets it propagate smoothly through space. Together, they create a language that describes both matter and motion. Every color, every reflection, every shadow is part of that language, variations in frequency, wavelength, and intensity that encode information about the world. Photons move at a constant speed in vacuum, about 300,000 kilometers per second, regardless of their color or source. That constancy defines the structure of space and time. According to Einstein's theory of relativity, this fixed velocity sets the ultimate limit for all motion and communication in the universe. No matter how fast an observer moves, the speed of light remains the same. It is not light that changes, but time and distance themselves that adjust to preserve it. This constancy explains why photons experience no passage of time. From their perspective, if they could have one, the journey from star to eye happens in an instant. For the rest of the universe, it may take millions or billions of years. Light connects points across vast distances without aging, turning space into a single continuum of interaction. Every photon also carries momentum, even though it has no mass. When it strikes a surface, it can exert pressure, the reason sunlight can push comet tails or power solar sails. This phenomenon, called radiation pressure, illustrates how energy and motion intertwine. Photons have no rest mass, yet their energy and direction make them capable of shaping matter across astronomical distances. The same light that warms a planet can, over time, move dust in space or propel spacecraft beyond Earth's orbit. The photon's language is universal. It speaks in frequency and wavelength, in reflection and refraction, in interference and polarization. From the glow of a candle to the blaze of a quasar, every expression follows the same principles. Light is both the simplest and the most eloquent communication in existence, the universe talking to itself through vibration. When you see sunlight sparkle on water or pass through a prism, you are watching physics translate into beauty. Each color that emerges is a sentence in that ancient language, describing not only energy but structure and rhythm. Understanding light's dual nature is to glimpse how all things connect, the microscopic and the cosmic, the measurable and the seen. In learning to read that language, we learn to see the universe as it truly is, one continuous dialogue carried by waves that never tire. As photons leave their star, they pass through a final veil, a region of charged particles streaming outward in all directions. This is the stellar wind, a constant flow of plasma made of protons, electrons, and atomic nuclei pushed into space by the pressure of light and heat. The sun's version of this wind fills the solar system, shaping magnetic fields, carrying energy, and influencing every planet within its reach. For light, it is the last reminder of its birthplace before entering true interstellar space. The stellar wind is not uniform. It varies with solar activity, magnetic storms, and the cycles of the star's rotation. Embedded within it are magnetic fields twisted and tangled by the motion of plasma. As light moves through this region, it can interact with these fields, its path slightly altered, its polarization changed. Polarization refers to the direction in which light waves oscillate, and stellar winds often imprint specific polarization patterns on the escaping light. Astronomers study these patterns to deduce the structure of magnetic fields far beyond our direct reach. The interaction between light and charged particles creates a subtle dialogue. In areas of high magnetic intensity, light may scatter differently, causing the star's glow to flicker or appear dimmer. The same process explains why starlight sometimes twinkles when viewed from Earth, though in our case, the final distortion comes from our atmosphere rather than interstellar plasma. Through these minute fluctuations, nature reveals the invisible threads of magnetism that weave through space. The solar wind also interacts dramatically with planets. When it encounters Earth's magnetic field, most of the charged particles are deflected, forming a protective bubble called the magnetosphere. Some particles, however, become trapped along magnetic field lines near the poles, where they collide with atmospheric gases. These collisions excite molecules, which release light as they return to normal energy levels. The result is the aurora, shimmering curtains of green, red, and violet light dancing across polar skies. Though this glow originates from matter rather than pure starlight, it is powered by the same energy that once left the sun as photons. The balance between radiation pressure and gravity is also evident here. Light itself pushes matter outward, while gravity holds it in. The stellar wind exists where these forces meet in equilibrium. Over billions of years, this gentle outflow carries away part of the star's mass, redistributing elements across interplanetary space. Dust and ions from ancient stars eventually become part of new systems, contributing to planets, moons, and even living organisms. The light that passes through the wind today may one day illuminate worlds formed from the remnants it helped disperse. At great distances, the stellar wind blends into the surrounding interstellar medium, where its speed finally slows to match the motion of the galaxy. Beyond that boundary, light continues almost undisturbed. The photons have now crossed from a realm of influence into near-perfect freedom. Their wavelengths remain constant, their paths straight except when gravity bends them slightly. They carry with them the story of their origin, a record encoded in their spectrum, polarization, and intensity. For us, that story becomes observable data. The faint color shifts and polarization of starlight tell scientists about stellar temperatures, compositions, and magnetic patterns. Every photon that reaches a telescope carries part of this coded message, allowing us to reconstruct the behavior of stars that are trillions of kilometers away. Light thus acts as both traveler and reporter, its interactions along the way adding nuance to the account it delivers. As photons finally leave the influence of their parent star, They enter the deep quiet between systems. Here begins the longest chapter of their voyage, the crossing of interstellar space. There will be few encounters now, only the slow spread of their wavefronts into the dark. Yet even in silence, light continues to communicate, filling emptiness with meaning, carrying within it the rhythm of the star that set it free. Once light clears the domain of its parent star, it enters a realm almost devoid of matter. The distances between atoms become vast, measured not in meters but in kilometers. This is the interstellar medium, a near vacuum so empty that a single cubic centimeter may contain just one lone atom of hydrogen. Yet even here, in this seeming void, light continues to interact, faintly, subtly, but continuously, with traces of dust and gas scattered across the galaxy. A photon travels in straight lines, moving at a constant speed through the vacuum, but the scale of its journey redefines our sense of motion. The distances are so great that even light, which circles Earth 7 times in 1 second, needs years to reach the nearest star and thousands to traverse the Milky Way. Across these gulfs, stars appear frozen, their twinkling an illusion of local air, not of cosmic motion. Light crosses time itself, revealing the deep stillness of expansion. Between stars, grains of silicate and carbon drift like faint smoke. Though rare, they are enough to dim and redden light, a process called interstellar extinction. Dust scatters shorter blue wavelengths more strongly than red, so starlight that passes through thick clouds emerges warmer in color. The faint orange tint of distant stars is a sign of this invisible filtering. Spectroscopy, the analysis of light spectrum, allows astronomers to detect such changes, revealing both the composition and density of intervening dust. These minute interactions help map the galaxy's structure. Light absorbed at specific wavelengths leaves narrow, dark lines in the spectrum, signatures of atoms and molecules along the path. Hydrogen, calcium, and sodium each mark their presence with precision. By studying these spectral lines, scientists can measure temperature, motion, and even turbulence within interstellar clouds. Light, though weakened by the journey, becomes a diagnostic tool, turning emptiness into a readable field of information. But for the photons themselves, there is only continuity. They do not slow, tire, or age. They carry on through regions that no spacecraft has yet reached, crossing distances so enormous that human imagination strains to follow. In the void, their wave fronts expand endlessly, their energy spread thin yet undiminished in purity. Each photon continues, as if unaware of the ages passing around it, maintaining the same rhythm, the same velocity, the same silent purpose. The calm that defines this region mirrors a different kind of stillness, the kind that invites rest. Just as light travels effortlessly through the emptiness between worlds, your thoughts can drift between moments without resistance. There is no need to reach any destination. In both the mind and the cosmos, distance becomes serenity, and motion becomes peace. If sleep begins to settle as you listen, let it come softly, the way light glides through space, without sound, without interruption, unhurried and complete. Even in this emptiness, the universe is not entirely dark. Background radiation, the collective glow of countless stars and galaxies, fills the void with a faint illumination. It is the subtle heartbeat of existence, present everywhere, reminding us that no point in space is truly separate from another. Every photon, no matter how isolated, belongs to a continuous stream connecting the past to the present, the near to the far. Eventually, some of these travelers will reach their destinations, a dust grain, a planet's atmosphere, or an eye turned upward in wonder. But most will continue indefinitely, their path unbroken. They are the purest expression of constancy, motion without fatigue, energy without decay. Their journey defines distance itself, setting the scale by which the universe measures its own immensity. When we observe starlight, we are witnessing this endurance made visible. The glow of a single star across countless light years is proof that the universe preserves what it creates. The photon that began in a fiery core ends its voyage as a moment of awareness. Between those 2 points lies only motion, patience, and silence, the true language of space. Though light seems to move in straight lines, the fabric of space it travels through is not perfectly flat. Wherever mass gathers, in stars, planets, or galaxies, space-time itself curves. Light, following this curvature, appears to bend. The concept may seem abstract, but it defines one of the most profound truths in modern physics. Gravity does not pull, it shapes. Einstein's theory of general relativity revealed that what we call gravity is the geometry of space-time. Massive bodies create indentations in this fabric, and light, always moving along the shortest possible path, naturally follows those curves. To an observer, that path looks bent, as though gravity had tugged on the photon, yet no force acts directly on it. Light simply obeys the shape of reality. This phenomenon is known as gravitational lensing, and it has transformed our ability to study the universe. When light from a distant galaxy passes near a massive cluster of galaxies, the curved space-time around that cluster focuses and distorts the light. The result is an arc or ring of brightness, a magnified image of something otherwise too faint to see. Astronomers use this effect as a natural telescope, observing galaxies billions of light years away through the lenses created by intervening mass. Lensing comes in many forms. Strong lensing produces dramatic multiple images, like the Einstein cross, where one distant quasar appears as 4 identical points around a foreground galaxy. Weak lensing is subtler, stretching background galaxies into faint ovals that reveal invisible matter along the line of sight. On the largest scales, mapping these distortions exposes the hidden skeleton of the cosmos, the vast web of dark matter that neither emits nor absorbs light, but dominates the universe's mass. Even light from our own sun bends under gravity. During a solar eclipse in the early 20th century, astronomers photographed the positions of stars near the darkened sun and found them slightly shifted, exactly as Einstein had predicted. That small deflection confirmed his theory and changed our understanding of the cosmos forever. Light, which had once been seen as immune to gravity, became its most eloquent witness. The bending of light also affects time. In the presence of strong gravitational fields, time itself flows differently. Photons climbing out of a deep gravitational well lose energy, their wavelengths stretching into redder tones, an effect known as gravitational redshift. Light falling inward does the opposite, gaining energy and shifting toward blue. These shifts are tiny in everyday conditions but immense near dense objects, such as neutron stars or black holes, where gravity approaches its extreme. Nowhere is this interplay more striking than around a black hole, where light can orbit or become trapped entirely. At a certain distance, the event horizon, even photons cannot escape. The boundary marks the limit of information. What happens inside remains forever hidden. Yet just outside that horizon, gravity bends light so sharply that observers can see the back of the black hole's own accretion disk curved into a glowing ring. In those shapes, we witness geometry turned visible, space-time folded into light. Gravitational lensing and redshift are not distortions in a chaotic sense. They are the natural expression of curvature. Light always follows the rules, tracing the contours of energy and mass with perfect fidelity. Each deflection is a clue, each shift a message. By studying them, scientists reconstruct the unseen architecture of the cosmos, the silent dialogue between light and gravity that defines the universe's structure. When we look into deep space, we do not see straight lines but curved stories, photons that have taken long detours through invisible valleys of space-time. Their bending tells us not only where matter lies, but how the universe itself is shaped. Through them, gravity becomes visible, and light becomes its patient messenger. Every photon carries within it a silent record of motion. As it travels through the universe, space itself expands, stretching the very wavelength of the light. This gradual elongation is called cosmological redshift, and it provides one of the most powerful tools in modern astronomy. Through it, light reveals not only the distance to its source but also the history of the universe's growth. The idea began with the discovery that galaxies are receding from one another. When scientists measured the spectra of distant galaxies, they found that their characteristic absorption lines, patterns created by elements such as hydrogen and helium, had shifted toward the red end of the spectrum. The farther away the galaxy, the greater the shift. This observation implied that space was expanding, not through motion of galaxies through space, but through the stretching of space itself. Redshift is, in essence, light's record of cosmic expansion. As space grows, every wave of light traveling through it grows longer. The photon's energy decreases slightly, but its speed remains unchanged. No force acts upon it. Rather, the arena through which it moves is itself enlarging. Imagine a pattern painted on a balloon. As the balloon inflates, the pattern stretches, though the paint does not move across its surface. The universe behaves in a similar way, and light stretches quietly along with it. This stretching gives us a measure of distance and time. By calculating the amount of redshift, astronomers can estimate how long the light has been traveling and how far it has come. Light from nearby galaxies may be only slightly shifted, while light from the most distant reaches of space has been stretched so much that it now lies in the infrared or even microwave range. The deeper we look, the older the light, allowing telescopes to peer back billions of years to the universe's earliest eras. This effect also serves as a cosmic chronometer. Because the expansion rate of the universe changes over time, redshift provides clues about its evolution. Observations have shown that the expansion is not slowing, as once expected, but accelerating, driven by a mysterious influence known as dark energy. Though invisible and poorly understood, dark energy appears to make up most of the cosmos, determining its ultimate fate. Light, stretched across this expanding framework, becomes our only direct witness to the process. Even the night sky's darkness carries this signature. The faint afterglow of the Big Bang, the cosmic microwave background, began as brilliant radiation that has been redshifted over 13 billion years into a near-uniform microwave hum. Every patch of that glow is light altered by expansion, preserving the earliest information we can observe. In studying its temperature variations, scientists map the seeds of galaxies and the geometry of the universe itself. Cosmological redshift is distinct from other forms of spectral change. A moving object, such as a star or planet, creates a Doppler shift, similar to how a siren's pitch changes as it passes. But redshift from cosmic expansion affects all of space, not just local motion. It is not caused by objects traveling through space, but by the stretching of space between them. Light, ever faithful to its environment, adjusts its wavelength as the universe grows. In a sense, the universe leaves its fingerprint on every photon. Each one tells a story of distance, time, and transformation. When scientists analyze that faint shift toward red, they read the history of everything, how galaxies drift apart, how the cosmos cools, and how energy becomes thinly spread across the infinite. Through these silent signals, we learn that change is not an interruption in the universe, but its defining rhythm. As photons continue their long journey, stretched yet undiminished, they remind us that everything moves within a larger expansion. Nothing stands still, not light, not time, not even the fabric of space that carries them. To observe the universe is to observe growth itself, written in the soft crimson tint of its oldest light. Long before there were stars, planets, or even galaxies, the universe was filled with light. But in its earliest moments, that light could not travel freely. The cosmos was dense and hot, a fog of charged particles, protons, electrons, and photons endlessly colliding. In that ancient plasma, light was trapped, scattered in every direction, unable to move more than a fraction of a millimeter before meeting another particle. The universe glowed, but nothing could see it. As the universe expanded, it cooled. Eventually, it reached a threshold where matter and light could separate. About 380,000 years after the universe began, temperatures fell low enough for protons and electrons to combine into neutral hydrogen atoms. This event, called recombination, changed everything. For the first time, the fog cleared. Photons were no longer trapped by free electrons. They began to move unimpeded through space, and they are still traveling today. That first free light forms the cosmic microwave background, or CMB, the oldest radiation we can observe. It fills the universe evenly, a faint whisper from the time when darkness first became possible. Though its wavelengths have been stretched by expansion into the microwave range, the CMB remains astonishingly uniform, with a temperature of about 2.7 Kelvin above absolute zero. This uniformity tells us that the early universe was smooth and balanced, differing by no more than a few parts in 100,000. Yet those tiny differences, slight variations in temperature and density, were the seeds of structure. Over billions of years, gravity amplified them. Regions that were slightly denser attracted more matter, forming clouds that would collapse into stars and galaxies. The uneven glow of the CMB, measured in minute ripples, is a photograph of potential, a cosmic blueprint showing where everything we see today began to form. Detecting this ancient light was one of the greatest achievements in science. In the middle of the 20th century, two radio engineers, Arno Penzias and Robert Wilson, accidentally discovered the faint microwave hiss while testing a large antenna. It was uniform across the sky and constant through time. They had stumbled upon the afterglow of creation itself. Later satellites, COBE, WMAP, and Planck, mapped that radiation in exquisite detail, transforming it from noise into history. The CMB confirms many key predictions of cosmology. Its spectrum matches that of a perfect blackbody, proving it originated from a time when matter and radiation were in equilibrium. Its temperature tells us how much the universe has expanded since that era. Its small irregularities reveal both the density of matter and the overall shape of space. From this single signal, scientists have built a detailed picture of the universe's infancy. In every direction we look, we see the same faint glow. It is not tied to any star or galaxy, but surrounds us as part of space itself. Every microwave photon reaching Earth today has been traveling for nearly 14 billion years, unimpeded, unaltered, except for the stretching of its wavelength. These photons are the oldest messengers we can receive, the light that began when the universe became transparent. There is a quiet comfort in knowing that the sky still holds this memory. Even in the darkest regions where no visible stars appear, that ancient light persists. It connects all places, all directions, all times. The universe keeps a perfect record of its own awakening, not in words or symbols, but in temperature, wavelength, and direction, a language written in radiation. When we listen to the cosmic microwave background, we are hearing the universe's first whisper to itself. Every photon carries a note from that original chorus, still resonating through time. It is the echo of the beginning, the first light of freedom, still on its journey, still arriving. After the first light of the universe spread outward, matter began to gather again. Gravity, working patiently across millions of years, drew clouds of hydrogen and helium together until they collapsed under their own weight. In those dense pockets of gas and dust, new stars were born. These regions are called nebulae, vast, glowing clouds where matter and radiation weave the fabric of renewal. To observe them is to watch the cycle of creation continuing endlessly. Nebulae come in several kinds. Emission nebulae shine with their own light. Within them, young, massive stars emit powerful ultraviolet radiation that strips electrons from surrounding hydrogen atoms. When the electrons recombine, they release photons at specific wavelengths, producing a deep red or pink glow, dominated by the hydrogen alpha line. This is what gives the Orion Nebula its color, a living workshop where new suns ignite. Reflection nebulae glow differently. They do not emit light but scatter it, reflecting the radiation of nearby stars. Their color tends to be blue because shorter wavelengths scatter more efficiently. The famous Pleiades cluster, surrounded by soft blue mist, is an example. In contrast, dark nebulae block light entirely, thick with dust dense enough to absorb radiation. These appear as silken shadows across the Milky Way, hiding the stars forming within. Only infrared telescopes can pierce their veil, revealing embryonic suns invisible to human eyes. Every nebula represents a dialogue between light and matter. Radiation from newborn stars shapes the gas around them, sculpting pillars, arcs, and cavities. The famous pillars of creation, captured by the Hubble Space Telescope, are columns of gas eroded by intense stellar winds and radiation pressure. Inside their shadows, new stars continue to form, hidden yet nurtured by the very light that carves away their surroundings. This interplay of destruction and creation defines the rhythm of galactic life. Nebulae are also chemical laboratories. Within their cooling gases, elements forged in earlier generations of stars mix and recombine, forming molecules of carbon monoxide, ammonia, and even complex organic compounds. These molecular clouds are the birthplaces of the building blocks of planets and eventually of life itself. Each generation of stars enriches the next with heavier elements, oxygen, carbon, iron, spread by supernova explosions. Light not only illuminates these processes but also records them, allowing scientists to read the history of chemical evolution across the cosmos. When astronomers observe these clouds, they are seeing time layered within space. The light that reaches us left its source thousands or millions of years ago, carrying the record of formation in progress. Spectroscopy reveals temperatures, densities, and compositions, letting researchers reconstruct the invisible dynamics of birth and decay. Even the colors themselves, the reds of hydrogen, the greens of oxygen, the blues of scattered light, tell stories of energy, temperature, and motion. Despite their beauty, nebulae are not tranquil. Inside them, shock waves, turbulence, and magnetic fields twist the gas into complex shapes. Light passing through these regions becomes polarized and scattered, its spectrum subtly altered. Every photon leaving a nebula carries a fingerprint of that chaos, a record of collisions, ionizations, and flows. From this information, astronomers can model how gravity and radiation sculpt galaxies over time. Yet beyond all the science, there is something timeless in these clouds. They are reminders that creation is never finished, that stars, planets, and even observers arise from the same interplay of light and dust. The atoms in our bodies were once scattered through such regions, illuminated by the same forces we now study. To look into a nebula is to look into our own past, a mirror of origins written in luminous gas and shadow. The journey of light through these stellar nurseries continues unbroken. Some photons will be absorbed and re-emitted thousands of times before escaping into open space. Others will be captured by dust and re-released as infrared glow. But many will leave entirely, continuing outward to cross interstellar darkness. They carry with them the memory of birth, the radiance of creation, preserved in motion. When light meets a planet, its journey becomes visible. What was once pure radiation moving through the void now turns into color, shadow, and reflection. Each world transforms starlight in its own way, depending on atmosphere, surface texture, and chemical composition. The result is a unique palette, the visible identity of a planet. Earth, for example, scatters light in its upper atmosphere. Molecules of nitrogen and oxygen deflect shorter wavelengths more efficiently, sending blue light in all directions. This Rayleigh scattering gives the sky its color and paints distant horizons in pale shades of azure. Mars, by contrast, is coated with iron-rich dust that reflects sunlight into warm oranges and reds. Venus hides behind thick clouds of sulfuric acid, reflecting nearly all incoming light and shining as one of the brightest objects in the sky. Each variation reveals the balance between absorption and reflection, a planet's fingerprint written in scattered photons. Astronomers quantify this property as albedo, the fraction of incoming light a surface reflects. Snow and ice, with their bright crystalline structures, have high albedo, while oceans and forests absorb more, appearing darker. The global average albedo of Earth regulates climate. As ice melts and dark surfaces expand, more sunlight is absorbed, amplifying warmth. Thus, light is not merely an aesthetic presence but a participant in planetary equilibrium. The balance of reflection and absorption shapes temperature, weather, and habitability. In gas giants, reflection takes on new complexity. Layers of ammonia and methane clouds refract and scatter light in intricate ways, producing soft bands of white, blue, and beige. On Saturn, ice crystals within the rings bounce sunlight back with extraordinary efficiency, creating the planet's ethereal glow. Even the smallest moons become tiny mirrors, reflecting the character of their parent stars into the darkness. Light also reveals motion. As planets rotate, the reflected brightness changes rhythmically, a cosmic heartbeat that tells scientists about day length, cloud cover, and surface contrast. When a planet passes in front of its star, the slight dimming of starlight reveals its size and orbit. By analyzing the faint colors of the light that filters through a planet's atmosphere during such transits, astronomers can detect water vapor, methane, or carbon dioxide. Each measurement is a conversation between light and matter, decoded across unimaginable distances. Polarization adds another layer to this dialogue. When light reflects off a smooth surface, such as an ocean or icy plain, its vibrations align in a specific orientation. Instruments sensitive to polarization can detect these patterns and infer surface properties, even when direct imaging is impossible. A glint of polarized light on a distant exoplanet may one day signal the presence of liquid water, a subtle, shining hint of habitability. Beyond scientific data, there is a quiet beauty in knowing that color itself is an interpretation of light's journey. The blue of a sky, the red of a sunset, or the silver shimmer of a moonlit lake are not intrinsic colors but outcomes of scattering and reflection, interactions between photons and atoms that produce experience. The same principles shaping alien worlds create the hues that guide our days and moods. Each reflected photon carries with it a trace of the star it came from and the surface it touched. In this way, light becomes a bridge between worlds, a traveler that links the distant and the near, translating physics into perception. When we gaze upward or outward, we are not merely looking at light, we are looking at the history of interaction, the story of how matter reveals itself through brightness and shade. Among planets, moons, and clouds, reflection turns energy into meaning. Every glimmer is information, every color a line in the universe's visual language. Through reflection, light completes one of its many purposes: to make the invisible visible. Light not only reveals the world, it divides time. As Earth spins on its axis, sunlight and shadow alternate, creating the most fundamental rhythm in nature, day and night. Every living organism, from single-celled algae to humans, has evolved in step with this cosmic metronome. It is more than a cycle of brightness. It is a cycle of biology, guiding when we wake, eat, move, and rest. At the planetary scale, the cause is simple. Earth rotates once every 24 hours, bringing different regions into and out of sunlight, but the effects are profound. As dawn approaches, the first scattered rays of light strike the upper atmosphere, bending around the horizon before the sun itself appears. Molecules in the air scatter blue wavelengths, painting the sky in delicate gradations of color, deep indigo at the top, fading to soft gold near the horizon. The physics behind this beauty is Rayleigh scattering, the same principle that makes the daytime sky blue and sunsets red. The arrival of light triggers a cascade of biological responses. In humans, photoreceptors in the eyes detect changes in brightness and send signals to the suprachiasmatic nucleus, a small region of the brain that serves as the master clock. This clock regulates the production of hormones such as melatonin and cortisol, synchronizing internal processes with the external day. Morning light suppresses melatonin, promoting alertness. As daylight fades, the absence of blue wavelengths allows melatonin to rise, preparing the body for sleep. These rhythms, called circadian cycles, are ancient. Even organisms that live deep in the ocean or underground carry remnants of the same timing system. It is a biological memory of sunlight, preserved in DNA. Our heartbeat, metabolism, and body temperature all adjust in subtle harmony with the turning of the planet. When artificial light or irregular schedules disrupt this rhythm, the body struggles to regain balance, proof that our biology still listens to the sky. The physics of Earth's rotation also shapes weather and seasons. As sunlight warms the surface unevenly, air and ocean currents redistribute heat from the equator to the poles. The resulting circulation patterns drive winds, storms, and the movement of clouds. Each sunrise begins a new phase in this planetary heartbeat, energy arriving, transforming, and radiating back into space. Every evening, as the planet's face turns away from the sun, stored heat escapes through infrared emission, cooling the air and restoring equilibrium. The line between day and night, the terminator, is always moving. From orbit, it appears as a soft shadow sliding continuously across continents and oceans. Astronauts describe it as a living border, neither dark nor light, but a gradient where both coexist. That moving edge defines the pace of time for all creatures below. Beneath it, cities awaken and fade, tides rise and fall, and countless biological clocks reset. For those listening now, this same rhythm flows quietly through you. The body senses not only the passage of hours, but the quality of light, its brightness, color, and angle. Evening light, rich in red and amber tones, signals the brain to unwind. As you hear these words, your eyes might grow heavier, your breathing slower. Sleep comes gently, carried by the same alternation that turns the planet itself. There is no need to chase it. The Earth's rotation has already set the pace. Light defines awareness, but darkness defines rest. Together, they create balance, activity and recovery, perception and peace. Just as the sun rises and sets, consciousness expands and contracts in daily rhythm. In this exchange between brightness and shadow, life maintains its harmony. When dawn returns, photons will again touch your skin, awakening ancient circuits within your body. Until then, night will hold its quiet dominion, guided by the same physics that governs the stars. The light visible to our eyes is only a small fraction of what truly exists. Beyond the narrow band of wavelengths that produce color lies an immense continuum, radiation both stronger and weaker than anything the eye can detect. This unseen world of hidden spectra reveals a universe that is far more dynamic, varied, and alive than human senses alone can perceive. On one side of visible light lies ultraviolet radiation. Its wavelengths are shorter, its energy higher, and its effects immediate. Ultraviolet photons can ionize atoms and break chemical bonds, which is why sunlight can burn skin and sterilize surfaces. Yet this same radiation is essential to life. It triggers the production of vitamin D in human skin and helps plants regulate growth. The ozone layer high in Earth's atmosphere absorbs most of the sun's ultraviolet output, acting as a filter that allows life to flourish below while shielding it from harm. On the other side lies infrared radiation, longer wavelengths that carry less energy but more warmth. All objects with temperature emit infrared light, from stars and planets to living organisms. Even the faint heat radiating from your body is a form of light, invisible to your eyes but detectable by infrared sensors. Telescopes tuned to these wavelengths can pierce cosmic dust that blocks visible light, revealing the hidden birthplaces of stars and the structure of galaxies cloaked in obscurity. The spectrum extends still further. Microwaves carry signals across the planet and trace the leftover glow of the Big Bang, the cosmic microwave background. Radio waves, with wavelengths that can stretch for kilometers, map cold hydrogen clouds and track the rotation of galaxies. These gentle frequencies reveal vast structures invisible in any other form, allowing astronomers to listen to the architecture of the cosmos. At the opposite extreme, X-rays and gamma rays expose the most violent events in existence: supernova explosions, neutron stars, and black holes devouring matter at the edge of physics. To the human eye, this diversity is hidden, yet technology has expanded our vision into these unseen realms. Instruments on Earth and in orbit translate invisible light into color-coded images. The fiery loops seen in solar photographs come from ultraviolet emission. The glowing filaments of distant galaxies appear through infrared sensors. Each wavelength contributes a different chapter of the same story, like musical notes forming one continuous harmony. Understanding hidden spectra has also transformed daily life. Infrared light powers remote controls and thermal cameras. Ultraviolet light sanitizes water and illuminates counterfeit markings. Microwaves heat food, radio waves connect continents. Every modern technology that communicates, measures, or observes is built upon photons that the human eye cannot see. The invisible has become indispensable. When we think of darkness, it is tempting to imagine absence, a void where light ends. Yet physics teaches the opposite. There is no true darkness, only wavelengths we have not evolved to perceive. The night sky, cold and silent to us, is filled with radiation spanning all frequencies, crossing paths and whispering data about creation. The cosmos is never empty. It is saturated with unseen light. For those listening now, this truth offers a quiet metaphor. Just as the visible spectrum is only a slice of reality, what we perceive in life is rarely the whole. Beneath what we can see, hear, or understand, there is always more, patterns waiting in the invisible. To rest is sometimes to trust that unseen motion continues, that energy flows even in silence. Light moves, whether noticed or not. The hidden spectra remind us that perception is not the limit of existence. From the warmth that surrounds you to the radiation that shaped the stars, invisible light fills every corner of the universe. It is the unseen fabric connecting matter and energy, presence and rest, revealing that the cosmos is always active, even when it seems perfectly still. Human eyes evolved to read a narrow window of the electromagnetic spectrum, wavelengths between roughly 400 and 700 nanometers. Within this small band, our world becomes colorful and comprehensible, but the rest of the spectrum, vast and rich, passes unnoticed. Beyond our sight, light continues to flow, carrying secrets that only instruments can reveal. To study these hidden forms is to extend our perception far beyond biology, to see through technology what nature concealed from our eyes. When X-rays were first discovered at the end of the 19th century, they revealed the invisible interior of matter. High-energy photons with short wavelengths can pass through soft tissue but are absorbed by bone and metal. In astronomy, the same radiation exposes violent events in the universe: exploding stars, colliding neutron stars, and disks of gas spiraling into black holes. Space telescopes like Chandra and XMM Newton detect these signals, mapping regions so hot that matter exists as plasma, a state of ionized gas reaching millions of degrees. Still higher in energy lie gamma rays, the most powerful form of light. Each photon carries energy millions of times greater than visible light, born in the heart of supernovae or from subatomic interactions. Gamma-ray bursts, lasting mere seconds, can release more energy than entire galaxies emit in a year. Instruments such as the Fermi Gamma-ray Space Telescope capture these fleeting flashes, transforming them into images of the universe's most extreme physics. Where visible light ends, gamma rays begin their work, showing us creation and destruction at cosmic scale. At the opposite end of the spectrum, radio waves stretch across kilometers. Their energy is gentle but their reach immense. Radio astronomy began in the early 20th century, when scientists detected strange noise coming from the Milky Way. Today, vast networks of antennas, such as the Very Large Array in New Mexico and the Square Kilometre Array under construction in Africa and Australia, join signals from multiple dishes to act as one enormous telescope. These arrays reveal cold hydrogen clouds, pulsars, and even the faint echo of the Big Bang itself. By listening to radio light, astronomers hear the deep heartbeat of the cosmos. Between the extremes, countless wavelengths fill the gaps. Microwaves tracing the background glow of creation, infrared showing star-forming dust, ultraviolet marking energetic young stars. Each band requires its own detectors and observatories, each translating unseen light into data humans can understand. Scientists assign colors to represent different energies, combining them into composite images that show the universe in ways no eye could ever perceive directly. The famous images of nebulae and galaxies, glowing with reds, blues, and greens, far beyond ordinary sight, are portraits built from invisible photons, made visible by interpretation. The extension of vision into these domains has changed how humanity understands itself. We no longer define the world by what we can see, but by what we can measure. Invisible light connects satellites, guides navigation, transmits communication, and diagnoses disease. It illuminates the weather, monitors crops, and explores planets. In the quiet rhythm of these signals, civilization itself depends on forms of light beyond sight. Even so, every discovery begins with the same principle. Light carries information. Whether visible, ultraviolet, radio, or gamma, each photon is a messenger, a quantized package of energy and truth. The universe reveals itself not through words or motion, but through the ceaseless flow of radiation across every scale of existence. As you listen, consider that all around you, countless waves are passing through space, walls, and even your body. They bring music, images, and invisible warmth. Though unseen, they fill every room, every moment. The world you inhabit is already radiant, with light the eyes cannot register. To know this is to see differently, to understand that darkness is never truly empty, and that illumination is more than what can be observed. Invisible light continues its quiet work, weaving energy, communication, and knowledge through the fabric of space. The eye is not the end of vision, it is only the beginning. As light travels farther from its source, it becomes fainter, stretched thin across the expanding fabric of space. Yet even at the edge of detectability, photons carry messages from worlds unimaginably distant. These signals from the edge allow us to look not only across space but backward through time, revealing the history of the cosmos written in light that has been traveling for billions of years. When we observe a distant galaxy, we do not see it as it is now, but as it was when its light began its journey. A galaxy 10 billion light-years away appears to us as it existed 10 billion years ago. Because nothing moves faster than light, observation becomes time travel, a window into the deep past. The farther we look, the younger the universe appears. In this way, telescopes function not merely as instruments of sight, but as chronometers, measuring time by distance. The Hubble Space Telescope revolutionized our understanding of this principle. Its deep-field images revealed thousands of faint galaxies in what once seemed empty sky, each representing a snapshot of the universe at a different age. Some of the light in those pictures began its journey before Earth had formed. Later, the James Webb Space Telescope extended this reach into the infrared, detecting the first galaxies that emerged from cosmic darkness after the Big Bang. The photons it captures are ancient travelers, their wavelengths stretched by expansion, their energy diminished but their information intact. Through these signals, astronomers study look-back time, the concept that observing light from different distances reveals different epochs of cosmic history. By measuring redshifts and brightness, they reconstruct the timeline of structure formation, how small fluctuations in early density grew into clusters, filaments, and galaxies. The universe becomes a living archive, each photon a record of a particular moment in its evolution. Even the faintest signals are precious. A single photon arriving in a telescope's detector may have journeyed across billions of kilometers of emptiness, passing through fields, dust, and gravity wells. The precision required to collect and interpret such data is extraordinary. Telescopes must cool their sensors to near absolute zero to minimize thermal noise, and spacecraft must shield instruments from radiation that could mask the delicate whispers of ancient light. Every measurement is a dialogue between patience and sensitivity. These distant photons also reveal how the universe is changing now. By comparing the redshift of faraway galaxies with their apparent brightness, scientists measure the rate of cosmic expansion and its acceleration. This led to the discovery of dark energy, the mysterious influence driving galaxies apart faster than gravity can restrain them. Once again, light serves as both messenger and mapmaker, showing not only where things are but how the universe itself evolves. On the scale of billions of light-years, even emptiness glows faintly. Diffuse radiation from countless sources blends into a cosmic background of starlight and dust. Astronomers call this the extragalactic background light, a collective memory of all the stars that have ever lived. By analyzing its intensity, they estimate the total amount of light emitted since the dawn of galaxies, a census of cosmic creation itself. For those on Earth, it is humbling to realize that every glimmer of night sky is an echo of the past. The photons that enter your eyes tonight left their stars long before human history began. Some may have traveled since the first atoms formed. To look at them is to participate in the universe's memory, to become the final destination of a journey that began when time was young. Light connects what exists now with what once was. Each photon that reaches us from the edge is an unbroken line between past and present, proof that the universe remembers itself through motion. In the faint shimmer of distant galaxies lies the oldest truth of all. Nothing that travels in light is ever truly lost. When astronomers look deep into space, they see that galaxies are not scattered randomly. They are arranged in vast filaments and clusters, separated by immense voids, where almost nothing exists. This pattern, delicate yet immense, is known as the cosmic web, the largest structure in the universe. It is a network of light and gravity, shaped over billions of years by the same physics that guides the motion of stars and planets. At the smallest scale, galaxies group together under mutual gravity, forming clusters. Clusters then link into elongated chains, stretching for hundreds of millions of light years. Between them lie great, empty regions, each so large that our Milky Way could fit inside thousands of times. When mapped through the light of millions of galaxies, this structure resembles the filaments of living tissue, threads of brightness connected by glowing nodes, woven through the darkness of intergalactic space. The cosmic web began as tiny variations in density within the early universe. After the release of the cosmic microwave background, regions slightly denser than average began to attract more matter. Over time, these areas grew, while less dense regions emptied out. Gravity amplified small differences into the vast network we see today. Matter flowed along invisible paths, forming a web that traces the shape of space-time itself. Where filaments intersect, galaxies form and light gathers, turning geometry into radiance. Much of this matter is not the familiar kind that builds atoms and stars. Observations suggest that most of the universe's mass exists as dark matter, unseen yet detectable through its gravitational effects. Light bends subtly around concentrations of dark matter, a phenomenon called weak gravitational lensing. By measuring these distortions, astronomers map the distribution of invisible mass, revealing the scaffold on which ordinary matter collects. The galaxies we see are only the bright traces of a deeper structure, glowing nodes on an unseen framework. In computer simulations, the evolution of the cosmic web looks almost organic. Filaments stretch and merge, clusters collide, and galaxies drift along gravitational highways. Over billions of years, the web becomes increasingly intricate, shaped by both dark matter and the expanding universe. The flow of light through this structure allows scientists to measure its scale, its growth, and its astonishing symmetry. The same mathematics that describes soap films and spider silk also governs the architecture of galaxies. Light acts as both witness and cartographer. When photons from distant quasars pass through these filaments, some wavelengths are absorbed by clouds of hydrogen gas. The resulting pattern, known as the Lyman alpha forest, appears as a series of thin lines in the quasar's spectrum, a barcode recording each encounter. By reading these patterns, astronomers can trace the density of matter along the photon's entire journey, reconstructing the shape of the web in 3 dimensions. The cosmic web reveals a paradox of scale. Its filaments are enormous beyond comprehension, yet governed by the same physical laws that shape droplets, waves, and cells. The forces that guide dust into spiral arms and electrons into orbit also sculpt the largest patterns in the sky. Through this unity, the universe shows that complexity arises from simplicity, and that gravity and light together weave order from randomness. To gaze at this structure is to glimpse the universe's skeleton, the hidden architecture that connects every star, every planet, every atom of matter. Light, moving along these paths, makes the invisible visible, translating geometry into brightness. It is both the thread and the tracer, flowing through the universe's design like current through a circuit. Somewhere within this web lies our own galaxy, one luminous point among countless others. Its starlight, too, travels outward, joining the grand network of illumination. Through the cosmic web, the universe holds itself together, not through rigidity, but through connection. The same principle governs the smallest life and the greatest space. Everything persists through relationship, and light is the medium that binds it all. Light may seem steady to the eye, but at its essence it is a pattern of oscillation, waves of electric and magnetic fields rising and falling in synchrony. When two or more light waves meet, their patterns overlap. Sometimes the peaks of one align with the peaks of another, amplifying brightness. Other times, peaks meet troughs, cancelling each other out. This dance of addition and subtraction is called interference, and it reveals one of light's most beautiful traits, its ability to create order through rhythm. The principle was first shown through Thomas Young's double-slit experiment. When light passed through two narrow openings and struck a screen, it did not form two bright spots, as one might expect from simple particles. Instead, it produced alternating bands of light and dark, an interference pattern. The bright regions marked where waves combined in phase, the dark where they cancelled. This simple observation confirmed light's wave nature and set the foundation for wave mechanics, optics, and later quantum theory. Interference occurs everywhere, though we rarely notice it. The shimmering color on a soap bubble arises from light reflecting off the front and back surfaces of the thin film. Some wavelengths reinforce each other, producing bright bands of color, while others cancel out. The same happens in oil films on water, in iridescent butterfly wings, and in the thin layers of a CD's surface. Each rainbow shimmer is a microscopic interference pattern, light composing itself into color through repetition and resonance. Beyond visible beauty, interference is the basis of precision in modern science. Holography records the interference between two light beams to capture three-dimensional information. Interferometers combine light from separate telescopes, allowing them to act as one instrument with the resolution of a much larger mirror. Through this technique, astronomers have measured the diameters of distant stars, detected exoplanets, and even observed gravitational waves, ripples in space-time itself. In laboratories, interference enables technologies such as laser gyroscopes, optical sensors, and atomic clocks. To understand interference intuitively, imagine two notes of the same tone played slightly out of sync. The sound alternates between louder and softer beats. Light behaves the same way, though its frequencies are far too high for the human ear to sense directly. Where waves align, brightness blooms. Where they oppose, darkness forms. From this interplay, light creates its own form of harmony, patterns of coherence and silence, structure within motion. Coherence is another crucial concept. For interference to persist, light waves must maintain a constant phase relationship, peaks and troughs arriving in predictable sequence. Ordinary light, such as sunlight or a lamp, contains many wavelengths, vibrating independently, producing a diffuse glow. Laser light, by contrast, is coherent. All photons move in step, their waves aligned. This coherence allows lasers to cut metal, scan the eye, and measure distances with astonishing precision. Coherence transforms light from scattered energy into unified purpose. On cosmic scales, interference also occurs among waves of different frequencies emitted by stars, gas clouds, and galaxies. Though individual patterns blur in the vastness of space, their combined rhythms shape what we perceive as luminosity and color. Light fills the universe not as a single note, but as a chord, countless frequencies resonating in quiet harmony. To witness interference is to glimpse nature's sense of balance. Light does not fight for dominance. It shares space, adding and subtracting gracefully until equilibrium appears. Within those alternating fringes of brightness lies a reminder that order arises not from uniformity, but from interaction. Every wave, no matter how small, contributes to the pattern of the whole. In understanding interference, we see that light is not merely movement, but relationship, oscillations, meeting and adjusting in perpetual dialogue. This dialogue forms the foundation of every reflection, every color, every sparkle that reaches the eye. Light, in its ceaseless interplay, composes the universe's quiet music, harmony written in waves. When daylight fades, the earth turns its face away from the sun, and the faint light of distant stars becomes visible. To the human eye, night seems dark, yet even darkness glows. The sky is never completely black. It holds the accumulated radiance of uncountable stars, nebulae, and galaxies, light stretched thin across the immensity of space. To look upward at night is to witness the balance between absence and presence, a reminder that even silence in the cosmos is filled with motion. The faint background light that persists after sunset is called the airglow. Molecules high in the atmosphere absorb solar energy during the day and slowly release it in darkness, emitting a dim green or red shimmer. Astronauts describe seeing it as a delicate band surrounding Earth, a soft halo of lingering sunlight. Added to this are the photons of countless stars, scattered by thin air and dust, creating the subtle radiance that allows the night sky to breathe rather than vanish. Human vision adapts to this low light through scotopic vision, guided by rod cells in the retina. These cells are sensitive to dim illumination but do not distinguish color. Under starlight, the world becomes a landscape of gray and silver, shapes defined by brightness rather than hue. Our eyes adjust chemically, increasing sensitivity as darkness deepens, allowing us to see by the faintest glow. This adaptation is an echo of ancient survival, the biology of creatures that learned to live by the rhythm of night and day. Light pollution has dimmed much of this view in modern times. Artificial lights scatter in the atmosphere, drowning the stars in a luminous haze. Yet where darkness remains, in deserts, high mountains, and the open ocean, the sky reveals its true form. The Milky Way arcs overhead like a pale river, its light the combined emission of hundreds of billions of stars. Each one contributes a photon here, another there, merging into a soft band that stretches across the heavens. The sight connects human perception with galactic scale, a bridge between the intimate and the infinite. At night, the absence of strong light also changes how we feel. The slowing of external stimuli encourages rest, reflection, and repair. Biologically, darkness triggers the pineal gland to release melatonin, signaling the body to prepare for sleep. Heart rate drops, body temperature cools, and metabolism shifts toward recovery. The body, like the planet, follows the turning away from light as a cue for renewal. To close the eyes is to mirror the earth itself, resting on its nightly rotation through shadow. For those listening now, this quiet rhythm is still present. The same photons that illuminate the night sky travel for eons before meeting your gaze, yet their arrival is silent, effortless. In that stillness lies an invitation to let thoughts drift like starlight through open space, to let breathing align with the slow turning of the earth. Sleep, when it comes, is not the absence of awareness, but its soft transformation, the mind dimming its brightness so that repair can begin. The science of the night sky is, in many ways, the science of patience. The dimmest stars visible to the human eye emit light that has been traveling for hundreds or thousands of years. Each one glimmers because it has endured. Between them, vast distances separate nothing from everything, yet light crosses them all the same. It moves continuously, silently, without haste. The universe teaches rest through example. When we look upward from a dark place, we see time made visible, light born before our ancestors walked the earth, still arriving now. Beneath that ancient glow, it becomes easier to let go of urgency. The mind, like the eye, can adjust to gentler brightness, finding comfort in the faint illumination that remains when everything else grows still. Let the night sky remind you, silence is not emptiness, and darkness is not the end of light. They are continuations in another form, calm, unbroken, eternal. After millions of years in open space, Light meets its first resistance. The photon approaches a planet, and its path bends slightly as it passes through the thin shell of gas surrounding it. This bending, or refraction, marks the beginning of its transformation from cosmic traveler to participant in a world's daily rhythm. On Earth, this interaction between sunlight and atmosphere shapes color, temperature, and time itself. The atmosphere is a complex optical medium composed primarily of nitrogen, oxygen, and trace gases. It scatters light according to wavelength. Shorter blue and violet wavelengths scatter most strongly, while longer red wavelengths pass more directly. This process, called Rayleigh scattering, is why the sky glows blue at midday and why sunsets blaze with red and gold. When the sun nears the horizon, its light travels through a thicker layer of air, losing much of its blue component and leaving the warmer tones that define twilight. Scattering is only one part of the story. As light enters air of varying density, its path curves slightly, causing the sun to appear higher in the sky than it truly is. This atmospheric refraction allows us to see the sun for a few moments after it has set below the horizon, its final rays refracted over the curvature of the Earth. The effect also produces mirages, illusions where distant objects or layers of air reflect light in unusual ways, making water appear where there is none. Every flicker of heat on a summer road, every shimmer above desert sand, is an optical conversation between photons and moving air. The atmosphere also acts as a filter. At high altitudes, molecules of ozone absorb most of the sun's ultraviolet radiation, shielding life from harmful energy. Water vapor and carbon dioxide absorb specific bands of infrared light, trapping heat and maintaining a stable climate, the greenhouse effect in its natural form. Without these selective absorptions, Earth's surface would swing between extremes of heat and cold, unable to support the life it now shelters. As sunlight passes through clouds, it undergoes Mie scattering, a process involving larger particles like water droplets. Unlike Rayleigh scattering, which favors shorter wavelengths, Mie scattering affects all colors more evenly, creating the bright whiteness of overcast skies. Each droplet becomes a miniature lens, bending and reflecting light in countless directions, softening shadows and diffusing brightness across the land. Through this gentle scattering, daylight becomes uniform and comforting, a visual balance that supports both life and perception. At dawn and dusk, these interactions reach their most dramatic form. The long path through the atmosphere filters out nearly all blue and green wavelengths, leaving the warm spectrum of amber, crimson, and violet. Tiny particles of dust and water vapor enhance these hues, painting skies that have inspired art and ceremony for millennia. Scientifically, it is a simple matter of wavelength and scattering length. Emotionally, it is a universal moment of connection, the planet turning, light changing, time renewing. Even after sunlight reaches the surface, its journey continues. It reflects from oceans, mountains, and leaves, each surface reshaping its spectrum. Some of this reflected light escapes back into space, joining the interplanetary glow visible to distant observers. In that sense, Earth too becomes a beacon, sending its own signature into the cosmos, blue from its oceans, white from its clouds, and green from its forests. A single photon striking the sea or a leaf completes a story billions of years long. The energy released in a distant stellar core becomes the warmth of a morning breeze or the glint on a drop of water. Every sunrise is the universe arriving again, bringing information, energy, and renewal to the surface of a single small planet. Through these daily interactions, scattering, refraction, reflection, light and matter collaborate to make the world visible. What we see each day is the evidence of that ongoing dialogue, written across the sky in changing color. Light's long journey ends not in exhaustion but in transformation. it becomes weather, vision, and life. Once light reaches the surface of a planet, it meets boundaries that decide its fate. Some photons are absorbed, their energy converted into heat or chemical change. Others bounce back into space, reflected from rock, ice, or water. Every surface performs this exchange differently, depending on texture, angle, and composition. Together, these interactions compose the dance of reflection, the choreography that turns raw radiation into color and form. The simplest type of reflection is specular reflection, which occurs on smooth, mirror-like surfaces. Here, the angle of incidence equals the angle of reflection. Light rays maintain their order, producing clear, crisp images. This is the reflection we see on calm lakes, polished metal, or glass. Each surface acts as a faithful translator of the world around it, sending photons outward in the same geometry with which they arrived. Most natural surfaces, however, are rough at microscopic scales. They scatter light in many directions, producing diffuse reflection. This scattering allows us to see objects from any viewpoint, regardless of where the light source sits. Paper, soil, and skin all reflect diffusely. The human face, for example, appears softly lit because light penetrates slightly into the skin before scattering outward, a phenomenon called subsurface scattering. Without it, features would look flat and artificial. Diffuse reflection gives the world texture, depth, and warmth. Another important factor is albedo, the measure of how much light a surface reflects overall. Snow and clouds have high albedo, returning most incoming light to space. Forests and oceans have low albedo, absorbing energy and appearing darker. These variations influence climate. High albedo regions cool the planet by reflecting sunlight, while dark surfaces absorb heat. As glaciers retreat and ice diminishes, Earth's average albedo decreases, amplifying warming, a subtle yet powerful feedback loop linking light to climate balance. Water introduces complexity. When sunlight hits the ocean, part of it reflects from the surface, especially at shallow angles, while the rest penetrates the water column. As light descends, red and orange wavelengths are absorbed first, leaving only green and blue to travel deeper. This selective absorption gives the sea its characteristic color. Waves and ripples continually shift the direction of reflection, scattering sparkles of brightness that trace the motion of wind and current. Each glint is a brief geometry of angles, the sun, the sea, and the observer aligned in perfect timing. Reflection also carries the phenomenon of polarization. When light bounces from a surface, its vibrations align in a preferred direction. Polarized sunglasses use this principle to block horizontal glare, reducing brightness from water or asphalt. Animals such as bees and cuttlefish can sense polarization directly, using it for navigation and communication. For them, the dance of reflection becomes a visible code written across the world. These physical processes combine to create the sensory richness we associate with beauty. The silver gleam of moonlight on a lake, the soft glow of a foggy morning, the shimmer of dew, all arise from the same interactions between photons and matter. The play of brightness and shadow, color and contrast, is physics performing art. Light's path is governed by equations, yet the result is poetry made visible. When reflected light escapes back into space, it carries with it information about the planet below. Observers orbiting far away could infer clouds, oceans, vegetation, and even seasons from its changing brightness. In this sense, reflection turns a world into a signal, a self-describing sphere of light. Earth, viewed from afar, tells its story through these variations, sending its identity outward with every turn. To witness reflection is to observe balance in motion. Every photon that departs leaves behind warmth or growth, Every absorbed ray contributes to life or weather. Light does not simply strike and vanish. It exchanges, transforms, and continues. The surface of a world is both mirror and participant, a meeting place where energy becomes experience. Light moves faster than anything else known, yet even that speed has a limit. In the vacuum of space, photons travel at about 300,000 kilometers per second. No signal, object, or force can exceed it. This constancy defines the structure of reality itself, connecting space and time into a single geometry. Before the 20th century, scientists believed that motion might change the speed of light. They imagined a stationary medium, an ether, through which light waves moved like sound through air. Experiments tested this idea by measuring how Earth's motion affected the speed of light. None showed a difference. The result was puzzling until Albert Einstein proposed a new framework, the theory of special relativity. Einstein's insight was simple but revolutionary. The laws of physics are the same for all observers moving at constant velocity, and the speed of light is identical for each of them. Time and space must therefore adjust to preserve that speed. A moving clock ticks more slowly, and lengths contract along the direction of motion. What changes is not light, but the way motion reshapes time itself. From these principles comes a remarkable consequence. Nothing with mass can reach light speed. As an object accelerates, its kinetic energy increases without limit. To reach the velocity of light would require infinite energy. Photons, having no rest mass, travel at that speed naturally, following null paths through space-time. Along such a path, no proper time elapses. To a photon, there is no before or after, only emission and absorption connected by geometry. Relativity also ties energy and mass through the famous equation E equals mc squared. This reveals that mass is a form of stored energy, and that even small amounts can yield enormous power. The equation explains the energy released in nuclear reactions and the brilliance of starlight itself. Fusion in a stellar core converts mass into energy, and that energy departs as photons, all moving at the same universal limit. The speed of light is more than a number. It is a boundary between what can and cannot communicate. Signals moving slower than light define cause and effect. Information cannot jump the gap between one moment and another faster than a photon could travel between them. This ensures the order of events, preserving the logic of causality throughout the cosmos. Einstein's equations predicted that light could be influenced by gravity, not through attraction but through curvature. Later observations confirmed that even time itself dilates near strong gravitational fields. Clocks on satellites tick slightly faster than those on Earth's surface because the planet's gravity bends space-time just enough to change the rate at which moments pass. Global positioning system satellites must correct for this difference constantly. Without those adjustments, navigation would drift by kilometers each day. The constancy of light speed, therefore, underpins every precise measurement we make, from astronomy to the device in your pocket. Physicists sometimes describe light speed as the speed of information. It represents the fastest way any influence can move through space-time. Even hypothetical particles proposed to exceed it, called tachyons, remain speculative, for they would violate causality itself. The universe protects its own coherence by holding light's velocity as its upper law. That constant speed also defines the scale of cosmic distances. A light year is not a measure of time but of space, the distance light travels in 1 year. When we say a star is 100 light years away, we are measuring not just length but history. The light we see tonight left that star a century ago. Every glance into the sky is a glimpse into the past, shaped by the same unbreakable limit. In this boundary we find symmetry. Light is both the messenger and the metric. It connects cause to effect, observer to event, present to past. The speed limit of the universe is not a restriction but a foundation. the rule that keeps time ordered, reality stable, and knowledge possible. Time is often imagined as a river, flowing steadily from past to future. Yet in physics, time is not independent of space or light. It stretches, bends, and slows in response to motion and gravity. The strange behavior of time is not illusion but law, woven into the very fabric of space-time. According to special relativity, time is relative to motion. When an object travels close to the speed of light, its clock runs more slowly compared with one at rest. This effect is called time dilation. It is not a trick of perception. It is measurable and real. Astronauts aboard high-speed spacecraft experience time fractionally slower than those on Earth. When they return, they are infinitesimally younger than their counterparts who stayed behind. Though the difference is small, the principle reshapes our understanding of simultaneity. There is no universal now shared across the cosmos. Each observer carries their own timeline, linked to their state of motion. Gravity adds a second dimension to time's flexibility. General relativity shows that mass curves space-time, and in doing so, it slows the flow of time itself. Near a massive object such as a planet or star, clocks tick more slowly than in empty space. This phenomenon is gravitational time dilation. On Earth it is subtle but measurable. A clock at sea level runs slightly slower than one on a mountaintop. Higher altitude means weaker gravity and therefore a faster passage of time. Satellites orbiting the planet experience both effects: faster time due to weaker gravity, slower time due to speed. Engineers must account for both to keep satellite navigation accurate. In extreme environments, the difference becomes profound. Near a black hole, gravity's curvature deepens until time nearly halts at the event horizon. To a distant observer, light emitted from near this boundary appears to slow and redden, fading into darkness. For the traveler falling inward, time continues normally, but the outside universe races ahead. Each frame of reference tells a different story, both true within its own geometry. Time is not a universal rhythm, but a local experience defined by gravity and velocity. These behaviors reveal that time and space form a single entity, space-time. The equations describing their relationship do not separate them cleanly, but treat them as intertwined coordinates of the same structure. The faster one moves through space, the slower one moves through time. A photon, traveling at light speed, moves entirely through space and not at all through time. Its existence links emission and absorption in a single, unbroken event. The distinction between then and now dissolves at that scale. Einstein's insight introduced a profound symmetry. The laws of physics are the same for all observers, but the measurements of time and distance depend on their motion. What once seemed constant, the ticking of clocks, the length of rulers, became relative, bound by the invariance of light speed. This relativity does not destroy order, it preserves it through transformation. It ensures that cause precedes effect in every frame, maintaining coherence across the universe. The strange behavior of time also extends to quantum physics. On the smallest scales, uncertainty governs when and how events occur. Particles can exist in superpositions, occupying multiple potential states until observation resolves them. In this microscopic domain, time appears less continuous, more like a sequence of probabilities than a smooth flow. Some physicists suggest that time itself may emerge from quantum interactions, a collective property rather than a fundamental one. If so, what we call now might be a pattern rather than a point. For everyday life, these distortions are imperceptible, yet they shape everything from GPS networks to the lifespans of cosmic rays entering the atmosphere. Time's behavior defines not only our measurements but our existence. Without it, motion would lose meaning, and light would have no destination. To recognize time as flexible is to realize that change is not uniform, and that the universe holds many versions of the same moment. The ticking of your heart, the orbit of a planet, the pulse of a distant pulsar, each keeps its own tempo, connected by the geometry of space-time. Time, like light, is both constant and variable, dependable yet endlessly adaptive. It does not merely pass, it participates. Every encounter between light and matter is a transaction of energy. When a photon strikes an atom, several outcomes are possible. It may bounce away, be absorbed, or pass through unchanged. These interactions, governed by quantum mechanics, are the foundation of chemistry, biology, and vision. The universe's visible complexity arises from this simple exchange, the conversation between radiation and substance. The basic rule is quantization. Light comes in discrete packets called photons, each carrying an amount of energy proportional to its frequency. Matter, in turn, consists of atoms with electrons arranged in quantized energy levels. When a photon's energy matches the difference between two of these levels, the atom can absorb it. The electron jumps to a higher orbit, storing the photon's energy within the atom. If the energy does not match, the photon passes by or scatters, continuing its journey. This selective absorption produces spectral lines, the fingerprints of elements. When white light passes through a gas, certain wavelengths are missing from the spectrum, absorbed by atoms within. Each element has its own pattern. Astronomers use these lines to identify the composition of stars, galaxies, and interstellar clouds. Through spectroscopy, light reveals the chemistry of places no probe could ever reach. After absorption, the excited atom does not hold energy indefinitely. It re-emits a photon as the electron returns to a lower level. The new photon may leave in a random direction or with slightly altered wavelength. This process, called fluorescence, transforms absorbed energy into light of longer wavelength. It explains the glow of minerals under ultraviolet lamps, the bright signs along city streets, and the luminous proteins used to study living cells. Even fireflies rely on it. Biochemical reactions excite molecules that then emit visible light. In solids, the story becomes more intricate. Atoms form lattices where electrons move collectively. In conductors, electrons flow freely, reflecting most light and producing metallic shine. In insulators, electrons remain bound, absorbing specific frequencies. Semiconductors fall between these extremes, controlling how photons interact with matter. Devices like solar panels, LEDs, and lasers depend on this balance. A photovoltaic cell, for instance, absorbs photons to excite electrons, generating electric current. The sun's radiation becomes motion of charge, light transformed into usable energy. Scattering adds another layer of behavior. When photons interact with particles much smaller than their wavelength, they change direction without losing much energy. This Rayleigh scattering gives the sky its blue color. When particles are larger, such as water droplets, scattering becomes Mie scattering, responsible for the whiteness of clouds and mist. In both cases, the process depends on particle size and wavelength, proving that the color of the world is a function of scale. The interaction between light and matter also drives thermal balance. Objects absorb radiation and emit it according to temperature. A perfect emitter, known as a blackbody, radiates energy at all wavelengths in a predictable distribution. Stars approximate blackbodies, their color determined by surface temperature. Cooler stars glow red, hotter ones blue. Planets, warmed by starlight, re-emit energy in infrared, balancing absorption with radiation. Without this equilibrium, worlds would freeze or overheat. In the microscopic realm, light can also influence motion directly. Photons carry momentum, and when they strike a surface, they exert a tiny pressure. Optical tweezers exploit this effect, using focused laser beams to trap and move single molecules. The same principle drives solar sails, allowing spacecraft to travel without fuel by harnessing the steady push of sunlight. When light meets matter, it ceases to be abstract. It becomes texture, temperature, and perception. Every color we see, every reflection, and every shadow are outcomes of this continual exchange. The boundary between illumination and substance is not fixed but active, where photons deliver energy and matter responds. In this balance lies the foundation of life. Photosynthesis, vision, and warmth all depend on this dialogue. Through it, energy from distant stars becomes movement, growth, and awareness. The meeting of light and matter is how the universe learns to see itself. Color is the human translation of light's wavelength into experience. It does not exist independently in nature as pigment or substance. It is a perception, a way the brain interprets the differing energies of photons that reach the eye. The physical world provides the spectrum. The mind turns it into sensation. Visible light spans wavelengths from roughly 400 to 700 nanometers. Shorter wavelengths carry higher energy and appear violet or blue. Longer ones are red. In between lie green, yellow, and orange, each corresponding to a particular range of frequencies. Together they form a continuous band, a rainbow of energy frequencies, ordered by wavelength but perceived as hue. When white light strikes an object, some wavelengths are absorbed while others reflect. The reflected combination determines color. A leaf appears green because chlorophyll molecules absorb red and blue light for photosynthesis and scatter the remaining green. A ripe tomato reflects red because its carotenoid pigments absorb shorter wavelengths. Even materials without pigment, such as bubbles or feathers, can produce color through structural interference, where the geometry of microscopic layers amplifies certain wavelengths and cancels others. The science of color perception begins with the human eye. The retina contains two main kinds of photoreceptor cells: rods, which detect brightness in low light, and cones, which respond to specific wavelength ranges. Most humans have three types of cones, sensitive to long, red, medium, green, and short, blue wavelengths. The overlapping responses of these cones allow the brain to reconstruct every shade we see. When only two kinds of cones function, color perception narrows. When all three are active, the full visible spectrum emerges. Light intensity also shapes color. Under dim conditions, cones grow less active and rods dominate, making the world appear bluish and desaturated, a phenomenon known as the Purkinje shift. Under bright light, cones recover, and colors return in full vividness. This adaptation shows that color is not an absolute property but a dynamic interpretation, continually recalibrated by the visual system. Beyond the eye, the brain plays an essential role. Neural circuits in the visual cortex compare signals from the cones, enhancing differences to heighten contrast. This process, called opponent coding, organizes color perception into pairs: red versus green, blue versus yellow, and light versus dark. It explains why certain combinations, such as reddish-green or bluish-yellow, cannot be perceived simultaneously. The mind builds color through comparison rather than direct measurement, translating physics into emotion. In nature, color serves many purposes. For plants, it attracts pollinators. For animals, it signals danger, health, or camouflage. The brilliant plumage of birds, the shifting tones of cuttlefish, and the spectral patterns on butterfly wings all arise from controlled interactions between light and structure. Even minerals gain their hues from trace impurities that absorb specific wavelengths. In every case, color is the result of light filtered by matter, interpreted by an observer. The origin of color also connects to temperature. According to blackbody radiation laws, the color of emitted light depends on temperature. Cooler sources glow red, while hotter ones shine white or blue. The sun's surface, at nearly 6,000 degrees Kelvin, produces a broad spectrum that peaks in green light but appears white because it includes nearly all wavelengths. Stars of different temperatures line the sky in shades of crimson, gold, and blue, each color a thermometer reading written in photons. Color's power lies not only in measurement, but in meaning. It shapes mood and behavior, guiding attention and memory. Blue evokes distance and calm, red suggests heat and urgency, green conveys growth. These associations arise from evolution and environment alike. Light has always been more than energy, it has been language. To perceive color, then, is to read the world's conversation with light. Each hue is a trace of an interaction, photon meeting molecule, wavelength meeting structure, signal meeting perception. The universe sends its energy in waves. Life turns them into experience. Color is the evidence that light, matter, and mind are parts of the same design. Light that has traveled for millions of years ends its journey in a fraction of a second when it reaches the human eye. The transformation that follows, from photon to image, is one of the most complex processes in biology. Vision turns physical energy into perception, bridging the external universe and the inner experience of awareness. The journey begins when photons enter the cornea, a transparent layer that bends incoming light to focus it toward the pupil. The pupil adjusts its diameter depending on brightness, expanding in dim conditions and narrowing in bright light to control the flow of photons. Behind it lies the lens, a flexible structure that fine-tunes focus through small muscular contractions. Together, cornea and lens project a sharp, inverted image onto the retina, a thin membrane lining the back of the eye. The retina contains about 120 million rod cells and 6 million cone cells. Rods are highly sensitive to faint light but cannot distinguish color. They dominate peripheral and nighttime vision. Cones, concentrated near the center in an area called the fovea, detect color and fine detail. Each cone type responds to a specific range of wavelengths, roughly corresponding to red, green, and blue, and their combined activity allows the brain to reconstruct every hue and shade. When a photon hits a photoreceptor, it triggers a cascade of chemical reactions. The key molecule, rhodopsin in rods and related opsins in cones, changes shape upon absorbing a photon. This change activates a signal that closes ion channels in the cell membrane, creating an electrical impulse. Unlike most sensory neurons, photoreceptors are continuously active in darkness and decrease their activity in light. This inverse logic improves sensitivity and dynamic range. These signals travel through a network of bipolar, horizontal, and ganglion cells, which process contrast and motion before leaving the eye through the optic nerve. The optic nerves from both eyes converge at the optic chiasm, where fibers from the inner halves of each retina cross to the opposite side of the brain. This crossover allows each hemisphere of the visual cortex to receive information from both eyes, creating a unified field of vision and depth perception. In the visual cortex, located at the back of the brain, billions of neurons collaborate to decode the image. They detect edges, shapes, movement, and color gradients, assembling fragments into coherent perception. The process occurs almost instantaneously, within less than 1/10 of a second, yet it involves continuous comparison, correction, and prediction. The brain does not passively record light. It interprets, filling in gaps, stabilizing motion, and reconciling differences between eyes. Vision also depends on adaptation. In bright light, pigment molecules break down and regenerate rapidly to prevent overstimulation. In darkness, sensitivity increases as rhodopsin accumulates again. This transition, called dark adaptation, can take up to half an hour. The moment when the night sky suddenly fills with stars after minutes of waiting is the biochemical threshold between blindness and clarity. Light does not act alone in perception. Eye movements, pupil adjustments, and neural feedback all modulate how photons become meaning. Even imagination uses similar neural pathways. The act of visualizing a memory activates patterns in the cortex, nearly identical to those triggered by real light. In this way, seeing is both physical and mental, an act of construction as much as reception. At the deepest level, vision is energy becoming awareness. Each photon absorbed by a receptor is an interaction between the external and the internal, the universe and the observer. When you look at the world, you are not merely detecting light, you are participating in its story, completing its journey through perception. The architecture of vision is thus more than anatomy. It is the bridge between matter and mind, between the measurable and the meaningful. Light governs not only what we see, but how we live. Every organism on Earth has evolved under the alternating pattern of day and night, synchronizing behavior and physiology with the planet's rotation. This rhythmic influence of light defines the circadian cycle, the internal clock that tells the body when to wake, when to eat, and when to rest. In humans, this cycle runs slightly longer than 24 hours and is reset each day by exposure to natural light. The key regulator is a region in the hypothalamus called the suprachiasmatic nucleus, or SCN. It receives direct input from specialized light-sensitive cells in the retina that respond not to color or detail but to brightness, particularly to blue wavelengths. When morning light strikes these receptors, they signal the SCN to suppress the hormone melatonin, increasing alertness and body temperature. As daylight fades, melatonin levels rise, lowering metabolism and preparing the body for sleep. This interplay between light and hormones creates the daily ebb and flow of energy. Cortisol peaks in the early morning to stimulate activity, then gradually declines. Core body temperature follows a similar rhythm, rising through the day and dropping at night. Even digestion and immune function are timed to this cycle. When artificial lighting or irregular schedules disrupt it, the body drifts out of sync, a condition known as circadian misalignment. The effects can include fatigue, reduced focus, and over time, metabolic strain. Light at night has a powerful effect because the retina's non-visual photoreceptors remain sensitive even when the eyes are closed or adapted to darkness. Screens and bright indoor lighting, rich in blue wavelengths, can delay melatonin production and shift the timing of sleep. To counter this, many devices now reduce blue light in the evening, while warm-toned light promotes relaxation. These adjustments mimic the color change of natural twilight, helping the body interpret the artificial environment as night. The circadian system is not unique to humans. Plants open and close leaves according to light levels. Coral reefs release eggs and sperm during specific lunar phases. Birds migrate by sensing subtle changes in day length. On a molecular level, almost every organism has genes that follow a roughly 24-hour rhythm. These clock genes regulate protein synthesis, cell repair, and metabolism, ensuring that biological processes occur at the most efficient times. For most of human history, sunlight was the primary signal of time. The invention of fire, and later electric light, expanded the day, but also softened the natural boundaries between wake and rest. Yet the body still listens to ancient cues: morning light through a window, the red tones of sunset, the slow darkening before night. Each acts as a whisper to the circadian clock, keeping it steady. For those listening now, these same patterns guide your own rhythm. The brightness of day once shaped alertness, while the dimming of light signaled the body to release its internal night. As you rest, melatonin spreads quietly through the bloodstream, Heart rate slows, and brainwaves lengthen. The mind begins to drift between awareness and surrender, following the same physics that governs stars and shadows. Sleep arrives not as escape, but as alignment, a return to the universal pattern of light and dark. Even during sleep, light continues to influence life. The faint glow of the moon can affect hormonal cycles and animal behavior, while deep darkness allows full restoration. This balance between illumination and shadow mirrors the equilibrium of the planet itself, one side turned toward radiance, the other toward calm. To live within this rhythm is to cooperate with the oldest order of nature. Every heartbeat, breath, and blink carries a trace of light's timing. The sun rises, the body wakes, the earth turns, and night returns. In that repetition lies stability, and in that stability, rest. Light is not only a natural phenomenon, it is the foundation of modern communication. Across glass fibers, through air, and deep into space, humanity uses photons to transmit information at nearly the speed of the universe itself. The same physical laws that govern starlight now carry the world's conversations, transforming light into language once more, this time by design. The cornerstone of optical communication is modulation, the controlled alteration of light's properties to encode information. A steady beam can vary in intensity, frequency, or phase, with each change representing a digital bit of data. When light passes through an optical fiber, these modulations travel as pulses of brightness and absence, forming binary code. Billions of these pulses can occur each second, transmitting entire libraries of knowledge through a strand of glass thinner than a hair. Optical fibers work through total internal reflection. The core of the fiber is made from high-purity silica glass, surrounded by a slightly less dense layer called the cladding. Light entering the core at a shallow angle bounces repeatedly within, guided along the length of the fiber with minimal loss. Because photons travel through glass rather than air, they remain shielded from interference, carrying signals over thousands of kilometers with astonishing efficiency. To ensure clarity, multiple wavelengths can travel through a single fiber simultaneously, a technique known as wavelength division multiplexing. Each wavelength carries independent data streams, allowing a single cable to handle vast amounts of information. Under oceans and across continents, networks of fiber optics now form the planet's circulatory system of knowledge. Every image, message, and voice that crosses the globe rides on guided light. At the microscopic scale, the transmission begins with a laser diode, a device that emits coherent light. Electrical signals drive the diode to produce pulses corresponding to digital data. On the receiving end, a photodiode converts these pulses back into electrical signals. The process may seem simple, but each photon's path is carefully managed through lenses, filters, and amplifiers to maintain coherence. Tiny differences in timing, measured in billionths of a second, can determine the fidelity of entire communication systems. Wireless systems also depend on electromagnetic radiation, though at longer wavelengths, radio, microwave, and infrared signals carry data through the atmosphere, bouncing from satellites to ground stations. The principles are identical: encode, transmit, receive, decode. In each case, the universe's fundamental constant, the speed of light, defines both the delay and the limit of connection. Even a signal sent to the moon takes about 1.5 seconds to return, not because of technology, but because of geometry. The precision of light-based communication extends beyond Earth. Deep space probes like Voyager and New Horizons use focused radio beams to send information across billions of kilometers. NASA and other agencies are now testing laser communication systems that will increase bandwidth by orders of magnitude, using narrow beams of light to transmit data directly from spacecraft to Earth. In this way, light, becomes both messenger and bridge between worlds. Within living systems, light also carries signals. Some animals use bioluminescence to attract mates or confuse predators. Fireflies flash in specific rhythms, anglerfish lure prey with glowing appendages, and marine plankton emit blue sparks when disturbed. These natural displays follow the same logic as engineered systems: energy converted to photons, photons interpreted as information. The medium is ancient, the meaning evolves. Each time a fiber glows beneath an ocean, or a beam links a satellite to a ground station, the continuity of light's journey persists. Photons born in the cores of stars now carry human thought, looping back into the cosmos that created them. The universe once spoke through light, now we speak back. For all its complexity, optical communication rests on a simple truth: information is a pattern carried by energy. Light, with its speed and purity, is the most perfect carrier nature provides. It connects continents, instruments, and minds. In every message sent and received, we extend the same principle that guides the stars: coherence, order, and connection through the motion of light. The world we perceive through light is vast, yet it remains a fraction of what truly exists. Human eyes evolved to capture only a small range of wavelengths, enough to navigate and survive, but not enough to see all that surrounds us. Beyond that narrow window lie signals that other species, and our own instruments, can sense, forms of vision that push past the limits of human sight. Many animals see light in ways we cannot. Bees and butterflies detect ultraviolet patterns on flowers, invisible to humans but vital for pollination. These patterns guide them like landing maps, pointing toward nectar and pollen. Some birds, including pigeons and kestrels, perceive ultraviolet reflections from feathers or urine trails, helping them recognize mates or prey. Reindeer see ultraviolet as well, which allows them to spot lichen glowing faintly against the snow. What we call white or colorless, they see as patterned and bright. At longer wavelengths, snakes and some beetles perceive infrared radiation. They sense heat as light, forming images of warm-blooded animals in total darkness. Pit vipers use this ability to strike accurately at prey even when no visible light is present. Fish and deep-sea creatures develop opposite adaptations, using bioluminescent signals or large pupils to amplify faint light where sunlight never reaches. Each species occupies a unique perceptual world, defined by the wavelengths it can interpret. Technology extends our reach into these hidden domains. Infrared cameras reveal heat signatures invisible to the eye. Night vision devices amplify faint light from stars. Ultraviolet filters uncover hidden markings on art or minerals. In astronomy, telescopes tuned to radio, X-ray, or gamma-ray wavelengths uncover phenomena that would otherwise remain unknown: pulsars, black holes, and the faint glow of intergalactic gas. Instruments act as extensions of the senses, translating unseen radiation into visible images, allowing humanity to visualize what nature concealed. The boundary between perception and reality is not fixed. Our sensory systems evolved for survival, not completeness. We detect what is necessary to find food, avoid danger, and recognize faces. The rest of the spectrum, though filled with information, remained invisible until curiosity and technology made it known. Through this expansion of sight, science gradually replaces limitation with awareness. Perception also involves the brain's interpretation of light. What we see is not raw data, but an internal model built from incomplete information. The visual system fills gaps, smooths edges, and filters detail to create stability. Optical illusions reveal this process. The mind invents motion or color where none exists, demonstrating that seeing is an act of construction. The edge of perception is therefore not only about wavelength but about cognition. the point where interpretation begins to overtake reality. In modern neuroscience, researchers can trace this construction down to milliseconds. The brain delays perception slightly, integrating information from the past tenth of a second to create a coherent present. We do not see things as they are now, but as they were moments ago, filtered through memory and prediction. Perception is thus a dialogue between light and time, between what enters the eye and what the brain expects to find. The same principle applies at cosmic scales. Every time we observe a distant star, we see it not as it is, but as it was when its light began the journey. The farther we look, the older the image becomes. The universe itself exists at the edge of perception, visible only through signals delayed by distance and expansion. To see the cosmos is to see memory in motion, energy carrying the record of its own past. For those listening, this edge can also be internal. As the eyes close and external light fades, perception turns inward. The mind continues to form images, shapes, and memories in darkness, proving that vision is not confined to the physical act of seeing. Just as telescopes extend awareness beyond the visible, rest extends awareness beyond waking. At both edges, the outer and the inner, light continues its work, shaping what is known and what can still be imagined. Every photon carries a record of its origin. Encoded within its wavelength, direction, and polarization lies the story of where it came from, how it traveled, and what it encountered along the way. Light does not remember in the conscious sense, but its behavior preserves information faithfully. Through that preservation, scientists can read the universe's past, an archive of events written in radiation. When light interacts with matter, it leaves measurable signatures. Reflected light reveals surface composition. Absorbed light records atomic transitions. Scattered light tells us about particle size and density. Even faint background radiation carries the imprint of its environment. In this sense, every ray of light is a messenger and a record, traveling across time with its evidence intact. By analyzing its properties, we reconstruct moments that have long since vanished. The spectra of stars provide some of the clearest examples of this cosmic memory. Each dark line within a spectrum corresponds to a specific atomic transition, allowing astronomers to identify elements present in the stellar atmosphere. From the width and shape of these lines, they can infer temperature, pressure, and motion. The tilt of the lines, caused by Doppler shifts, reveals whether a star is moving toward or away from us. Even rotational speed and magnetic fields can be extracted from the fine structure of the pattern. A simple beam of light, properly decoded, becomes a complete biography of its source. On a larger scale, light's memory extends beyond individual stars. The cosmic microwave background preserves the conditions of the early universe itself. The density variations, temperature fluctuations, and geometry of space-time during its infancy. Its nearly uniform glow carries subtle irregularities that describe the formation of galaxies and the overall shape of the cosmos. These patterns are not random, they are fossilized echoes, data stored in radiation since the first release of light. In laboratories on Earth, physicists explore the memory of light through spectroscopy and photon correlation. Lasers measure vibrations in molecules, revealing their structure. Astronomers use interferometers to detect tiny phase differences between light waves arriving from distant sources. Even the reflection of sunlight from Earth's atmosphere carries clues about vegetation, ocean coverage, and cloud patterns, a planetary fingerprint that could be recognized by observers light years away. Through these methods, light becomes both messenger and witness, recording without intent, yet revealing with precision. This inherent memory is tied to the principle of conservation. Energy and information are never lost, only transformed. When a photon is absorbed, its energy changes form, perhaps becoming heat, motion, or chemical potential, but the information it carried is not destroyed. In theory, if one could perfectly track every interaction, it would be possible to reconstruct every past event from the light that once scattered from it. The universe is therefore not forgetful. It simply distributes its record across immeasurable distances. In human experience, light's memory manifests through images and perception. Photons captured by the retina trigger electrical signals that the brain translates into visual memory. A moment of sight becomes a lasting pattern of neurons, a personal archive of illumination. Cameras and telescopes extend this act of remembrance, freezing light into data, preserving the unrepeatable instant when energy and form align. The memory of light is also emotional. The glow of sunrise may recall beginnings. The color of evening light may summon calm. Though these responses occur in the mind, they are grounded in physics, specific wavelengths, scattered by air, filtered by molecules, interpreted by consciousness. What begins as radiation ends as reflection, both literal and mental. Light's endurance across time invites a quiet thought. Nothing that shines is truly gone. The photons leaving Earth tonight will travel outward indefinitely, crossing the void long after their source has changed. Somewhere, perhaps far in the future, they may strike another surface and reveal a trace of this moment. In that way, light extends memory beyond the boundaries of life itself, turning impermanence into persistence. Every beam that travels, every reflection that lingers, contributes to this unbroken record. To observe light is to read the handwriting of the cosmos, energy inscribed with history, carrying the story of where it has been. Every story of light is a story of connection. What begins in the furnace of a star ends in the quiet surface of an eye. Between those 2 points stretches a distance so immense that it binds the cosmos and consciousness into one continuous act: emission, travel, reception, awareness. Light is the thread that links them all. In a stellar core, gravity compresses hydrogen until the pressure is so intense that atoms merge, releasing energy in the form of photons. Those photons scatter, absorb, and re-emit countless times before escaping into open space. Some will travel for millions of years, passing dust clouds, gravitational fields, and planetary atmospheres, each encounter altering their direction or spectrum but never their fundamental nature. When at last one reaches a living world, it carries with it the signature of its origin, a memory written in energy. On Earth, that photon may strike a leaf and drive photosynthesis, feeding an entire ecosystem. It may warm ocean currents or reflect from a glacier. Or, by chance, it may enter an eye and end its journey in perception. The same energy that began in a nuclear reaction becomes a human thought, an image, an emotion. Physics and biology converge in that instant, the external universe meeting the inner one. The path of light through an atmosphere shapes what we see, scattering blue into the sky, reddening the horizon at dusk. Once inside the eye, the photon transforms again, turning into an electrical impulse, then into neural patterns in the visual cortex. Within fractions of a second, the brain assembles meaning, form, color, memory. A photon's billion-year journey becomes an instant of awareness. The scale collapses, and the universe becomes personal. Across civilizations, light has been both a tool and a metaphor, the source of knowledge, clarity, and renewal. Yet beneath the symbolism lies the same physical truth. Light makes vision, warmth, and life possible. Its constancy defines time, its speed limits communication, its interaction with matter shapes everything we perceive. From galaxies to human experience, light is both messenger and medium, carrying information outward while creating meaning inward. As understanding deepens, humanity learns to speak back through light. Lasers send messages across oceans and into space, Sensors capture distant starlight and decode its structure. The same principles that guide photosynthesis and sight now guide communication and exploration. Every technological advance extends the same relationship, energy turned into knowledge through interaction. When the day ends and sunlight fades, the body begins to mirror the turning of the earth. Photons grow scarce, melatonin rises, and the mind starts to release its hold on external brightness. The visual world softens, edges dissolve, and light continues its journey inward, transformed once more, not into image or signal, but into rest. The rhythm that governs stars also governs sleep, a gentle oscillation between radiance and stillness. For those listening now, every quiet moment of closing the eyes echoes a universal pattern. The energy that once crossed interstellar space now becomes calm within you. Each breath slows, the mind follows, and thought drifts like the fading afterglow of sunset. Light has reached its destination, not in matter, but in peace. The voyage of light, from stars to eyes, is therefore the voyage of awareness itself. It begins in the heart of creation and ends in perception, reminding us that the act of seeing is part of the same process that builds worlds. The universe illuminates itself through observation. To look at the night sky is to complete that circuit. Starlight meeting consciousness, the cosmos recognizing its own reflection. When you next see the stars, remember that their light is already within you, carried by the same laws that shape them. Energy becomes vision, vision becomes understanding, and understanding becomes rest. The universe continues to shine, and within that endless glow lies the gentle invitation to close your eyes. We from Sleepy Stories wish you a good night.